The next talk is by Yoichiro Masuda from Jikei University School of Medicine, Tokyo. V1 projection zone signals in human macular degeneration depend on task, not visual stimulus.
Thank you. Pretty James, Chris. Thank you for organizing the talk. Today, I will focus on some interesting brain responses in patients with macular degeneration. This is a schema of human visual pathway. The optical input from the retina goes to the retinal geniculate nucleus via optic nerve, and then goes to the primary visual cortex via optical radiation. This is a post-mortem right brain. Here is calcarine sulcus. Our work focuses on this primary visual cortex V1 around the calcarine sulcus. This is a measurement of the visual field maps using fMRI and the expanding contrast rings. This is an inflated right hemisphere, front, back, corpus callosum, occipital pole, and calcarine sulcus. The peak response shifts smoothly from posterior to anterior calcarine as the ring grows expanding. This is a retinal topographical representation in V1, and the visual stimulus on the central retina evokes response on the end of the calcarine sulcus. The horizontal line projects to the bottom of the calcarine sulcus. The upper vertical line projects to the upper bank of calcarine, and the lower vertical line projects to the lower bank of calcarine. If a part of the retina is damaged, there is no visual input from the retinal region to V1, where is lesion projection zone LPZ. What happens in the LPZ neuron? First, degenerative and unresponsive. Second, reorganizing and remapping. Third, lay dormant due to stability. This is the example image that the subject with macular degeneration would see. They have a central retinal lesion, so they have a foveal scotoma. The lesion projects to the posterior V1 LPZ. In the absence of functional fovea, they develop a preferred retinal locus, PRL, in the peripheral retina. The signal from the PRL, blue, goes to PRL projection zone, PRPZ, which the patient uses as the usual fixating position. Excuse me. Can you see the The LPZ occupies a wide cortical area. The PRPZ is a narrow area due to the cortical magnification. In the paper, the literature on reorganization in human V1 in the case of macular degeneration contains several different conclusions. In the first report, Sannes et al. Describe an age-related macular degeneration AMD subject. They find a large unresponsive zones in the V1 LPZ. They concluded no evidence of reorganization. In a paper that followed slightly after this one, Baker et al. Described two juvenile macular degeneration JMD subjects in which nearly all of V1 is responsive. They concluded that the signals in the LPZ were evidence of large-scale reorganization. We were impressed by both of these findings, and we have wondered why there would be such a difference. We also measured the patient with juvenile macular degeneration, JMD. JMD1 was a 31-year-old female who was diagnosed with corneal dystrophy at age 18. The absolute scotoma extended over 45 degrees in diameter. This schema shows the retina, visual field profile, and V1 in right hemisphere. This subject had a central retinal lesion, which produces an absolute scotoma, a dark gray part, which projects to posterior V1 LPZ. The star part on the lower left visual field indicates a PRL. The PRL projection zone, PRPZ, is on the upper right anterior calcarine sulcus. Light gray shows the stimulus extent on the visual field. In control subjects, the stimuli fell on the same retinal location of the PRL of JMD1. We measured JMD subjects using full field drifting control pattern stimuli. These stimuli were moving to different directions, and the stimuli were grouped into two types of viewing conditions: passive viewing condition and one-back task condition. In the passive viewing condition, the subjects were instructed to just fixate the central dot and do no task during presenting of the stimulus. In the one-back task condition, the subjects were instructed to just fixate the central dot and do no task. In the one-back task condition, the subjects were instructed to press the button when they detected two consecutive repetitions of the same stimulus. These stimuli were shown in the block design. These are the results from passive viewing. The left panel shows the JMD subjects, and the right shows a control subject. The right occipital lobes are enlarged in here. The bold time series that measures the response in a circle of interest. In both JMD and control subjects, there was an expected response in the PRPZ and no or negative response in the LPZ. There are large unresponsive zones in V1. There is no evidence for reorganization or remapping. Next are the results from one-back task. The response in control subjects was very similar to the passive viewing data. This was not the case in the JMD subject. In JMD subject, there was a good response in nearly all of V1. The good response extended beyond the PRPZ, spreading into the LPZ. Signals from the LPZ are significant, but smaller than the PRPZ. The area near the occipital pole, which had negative board in passive viewing, now has positive board in one-back task. The only difference between these two conditions was the task. Thus, the task changes the ephemeral signal from negative to positive. This is not the case in the control subject. That's in JMD subject, but not the control subject. The activation extends into the LPZ. This activation is task dependent. Returning to the previous study, the literature contains several different conclusions. In the report of lack of reorganization, they used a checkable stimulus with passive viewing. In the report of large-scale reorganization, they used faces or object stimuli with one-back task. Together with our study, the answer of this question is, because the LPZ activation depends on the task. Now the following question arises. Is the visual stimulus necessary for task-dependent LPZ response? Next, we measured JMD subjects using tactile stimulus. The piezoelectric cells stimulate either left index or middle fingers. The primary somatosensory cortex is located in the postcentral gyrus of the parietal lobe. The stimuli were grouped into the two types of touching conditions, passive sensing condition and one-back task condition. In the passive sensing condition, the subjects were instructed to just perceive the tactile stimuli. In the one-back task condition, the subjects were instructed to press the button when they detected two consecutive repetitions of the same finger stimulation. During all experiments, the subjects closed their eyelids, so there was no visual input. These are the results from passive condition. The left panel shows the JMD subject and right shows the control subject. This is the bold response in a circular of lesion of interest in V1. The left and right column shows the bold response from V1 to FEF. In both JMD and control subject, there was an expected response in the somatosensory cortex, but no response in the entire medial occipital lobe. There are large unresponsive zones in V1. In one-back task condition, the response in control subjects were very similar to the passive condition data. But this is not the case in the JMD. In JMD subjects, there was a significant response in nearly all of V1. The only difference between these two conditions was the task. Thus, the task changes the fMRI signal from negative nothing to positive. Thus, in JMD subject, but not the control subjects, the V1 activation is manifested by the task. This activation was similar to that observed with visual stimuli. These activations are task dependent. Next, we examined JMD subjects using auditory stimulus. These stimuli change sound every second. The auditory cortex is located in the superior temporal gyrus in the temporal lobe. The stimuli were also grouped into the two types of hearing conditions, passive hearing condition and one-back task condition. In the passive hearing condition, the subjects were just heard the sound. In the one-back task condition, the subjects pressed the button when they detected two consecutive repetitions of the same sound. The subjects were also closed eyelids, so there was no visual input. These are the results from passive hearing. In both JMD and control subjects, there was an expected response in auditory cortex, but no response in nearly all of V1. Next are the results from one-back task. Only in JMD subjects, significant responses were observed in nearly all of V1 and also V2 and V3. Thus, the task changes the fMRI signal from unresponsive to positive. Thus, in JMD subject, but not the control subject, the activation manifested by task in auditory stimuli as well. A similar trend was observed in a total of 6 JMD subjects. Returning to the second question, because we have identified the task-dependent responses to tactile and auditory stimuli without visual stimulation, this means that visual stimulus is not needed. Here comes the next question. How should we interpret the LPZ response that is task-dependent and does not require visual stimulation? There is an interesting study in sighted subjects from Merabet et al. When sighted subjects were blindfolded completely for 5 days, V1 responded to a Braille character discrimination task. And when the blindfold was removed, the response disappeared. The tactile task evoked V1 response depends on the duration of visual deprivation and is reversible. This suggests that the tactile task evoked response could be explained by pre-existing neural circuits. This is a model to explain the task-dependent board modulations in V1 of the control subject. Primary signal from the LGN project to the main input layers in V1. The LGN also sends a gating signal that governs the effectiveness of feedback signals. In the control subjects, because there is still a very low retinal image contrast, both the primary and gating signals in V1 are nice. This is showing a task-dependent feedback signal. The LGN gating signal prevents this feedback from interacting with the noise. So there is no response in V1 in control subjects in our study. However, after 5 days of blindfold, the gating signal is reduced by a substantial amount, and task-dependent feedback signals can be transmitted into V1. On the other hand, in JMD subjects, because the retinal region is dysfunctional, both the primary and gating signals are absent in the LPZ. Without the gating signal, task-dependent feedback signals can be transmitted into V1. In the absence of feedforward signal in the patient's LPZ, we propose that the task-dependent feedback signals are dominant modulator of neuronal activity. The answer of this question, first one, because the LPZ can be activated by task, so we think that this means there is no degeneration in the LPZ. Second, if the LPZ is reorganizing and remapping, the LPZ should be evoked regardless of the task. However, because the LPZ is unresponsive in passive condition, we think that this means there is no reorganization in the LPZ. Third, we propose that task-dependent LPZ response is increased only because the deletion of the feed-forward signal unmasks the pre-existing feedback signal. We prefer this theory. I'd like to consider the implication for retinal and visual therapy for retinal degeneration patients. It is impossible to restore the visual field loss in retinal region by cortical reorganization. So we need visual therapy. For effectiveness of the visual therapy, cortical circuit needs no degeneration or preservation and reversible reorganization or preservation of pre-existing circuit. If there is cortical reorganization, the success of the therapy would depend on the degree of reorganization reversibility. However, if there is no substantial reorganization and the circuits are simply preserved, then the signals delivered by the therapy will be sufficient to restore the vision. Our results support preservation of the circuit. This research has been made possible by the cooperation of many collaborators. I'd like to thank them.
Yeah, very interesting concepts. Any questions to this? Yeah, go ahead, Preeti.
Hi, my name is Preeti Verghese. So I wanted to ask, can you tell us a little bit more about the LGN gating signal and, why you are hypothesizing that that has a role in?
Yes, the gating signal is our hypothesis, the signal of our hypothesis. That signal prevents the feedback signal by retinal input, including some noise.
For that. I actually believe your results completely, but I was very interested in evidence for the LGN gating signal.
I don't have any evidence. Sorry.
Yes, go ahead. Ione Fine.
Hi, I'm Ione Fine. I love this work. I really, really love it. It's a thought I only just had actually, so it's great hearing it, is you obviously, you see this, task dependence, which has these sort of fundamental implications for cross-modal plasticity, but I do wonder whether what you're measuring is a neural signal. So there's that work by Aniruddha Das showing that when you're expecting to do a task, you can get a blood flow response in the absence of a neural signal. And so in that case, what you're getting is actually a bold response, but you're not seeing an actual firing. Now, your results still have implications for all our work doing fMRI because we're all measuring blood flow. But I wondered whether you'd kind of it's the first time I'd put those two studies together and thought, oh, maybe they have a relationship to each other. Is that making any sense? Do you have a reason? Because your task seems very similar to the tasks that they use and to get a blood flow response without a neural signal. If that work you're not aware of, then we can just take this offline. It's kind of an obscure question. I'll take that as a offline. Or that my accent is too weird.
The blood flow alone. Only blood flow. Doesn't make sense to me. The neural control of blood flow.
Offline question.
Anyways, yes, go ahead. This is Mriganka, sir.
I am Mriganka, sir, from MIT. I actually think Ione's idea is quite interesting because it is not true that neurons control blood flow. Astrocytes do and pericytes do. Neurons never directly contact blood vessels. It is through the astrocyte mechanism, which astrocytes listen in on synaptic activity, and they regulate blood flow into the brain very, very astutely into active sites. You can have astrocyte activation without neuronal activation. And that is my reading of Aniruddha Das's work. So this is a very subtle issue, but it is possible that you can get, quote, activity in a lesion projection zone without having neuronal activity. I think that is Ione's point. And I think it's a very interesting point. You have to stick an electrode in there to show me that there is neuronal activity.
Let's take this up in the general discussion.
All right. Sorry. Yes.
Thank our speaker again.
Inspired by Ione.
Yeah.
That's all.
You three need to talk.
Yeah. Thanks very much.